SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we will be starting our lecture number 21, mechanical measurements. In the previous two lectures, we have been discussing some aspects of measurement of pressure. In fact, we looked at manometry, or the use of a liquid or a height of a liquid as a measure of the pressure using different types of manometers. We talked about the U tube and the well type with the straight tube and the inclined tube. We also worked out an example to demonstrate the working of such a manometer. After that, we started looking at other types of measurement of pressure, different types of gauges which can be used. We looked at the Bourdon tube as one of the cases. It is a mechanical instrument. And then we started talking about other types of gauges like the diaphragm gauge and the use of a strain gauge for measuring the deflection of a diaphragm. And we introduced some elementary ideas regarding this, including the LVDT. We discussed in very brief the nature of LVDT and how it is used to measure a deflection or a distance, which is the deflection due to the action of the pressure. So, in other words, the pressure signal is converted into a deflection or a length, and this length is measured using either the LVDT or a strain gauge. So, what I will be doing in this lecture is to confine myself more to a discussion on the strain gauge type of measurement of deflection. In fact, strain gauge can also be looked upon as an instrument which is used for measuring very small lengths. So, from that point of view, it is a very important metrological application. It has got very important metrological application, the measurement of length. And the measurement of length is somewhat simpler to understand, because length is basically a comparison. Length is defined as the standard length of an object which is kept under stated conditions of pressure and temperature, and this length becomes the unit with which we compare other lengths or lengths of other objects. So, the meter scale is actually the standard, international standard, which is used as actually, and the meter scale and its submultiples and multiples, they are used for measurement of length. So, metrology will of course be considered in more detail by another professor later on. Therefore, I will not go into details about metrological aspects of measurement of length. Briefly, I will touch upon the measurement of length as it is relevant to the measurement of pressure in this particular lecture. So, to look at what we are going to do, we are going to look at pressure tube with strain gauge, and then we will look at the strain gauge, its theoretical and practical aspects, something about the circuitry, and then if time permits, we will take a look at diaphragm gauge and then LVDT and so on. But I think we will just have enough time to look at more carefully or in more great detail the aspect of strain gauge as a measurement of as an instrument for measuring length and hence the pressure. So, if we look at the next slide, I have in fact shown a strain gauge element. It consists of, as you can see here, you see the wavy line here. The wavy line happens to be a material which is deposited or etched on a metal foil. Etched means the rest of the material is removed and only this amount of material which is shown here in the form of a zigzag is going to be present. And you see that it consists of sectors which are straight, and then there is a small bridge between the two straight segments, again another straight segment, and so on. So, the idea is to make a large length for the conducting material. This is the conducting material which is the metal foil, which is going to have a large length equal to the number of such u multiplied by twice the length of each segment. Okay. In other words, to obtain a certain required resistance, we are going to have the metal deposit etched metal in the form of a length equal to L, which consists of these units. Each unit is something like one straight, one bridge, small bridge here, another straight. This is one unit. So, we have 4 such units here, and therefore, the length of this will be equal to 8 times the length of each one of the vertical units. And the strain gauge element in the form of this wavy distribution of material is actually held by a backing material, and this backing material may be a made of plastic or paper or some such material, and this is going to be usually bonded to the surface whose strain we want to measure. The strain gauge is used to measure the strain of a surface on which the strain gauge is mounted. The assumption is that the wire which is shown here or the conductor which is shown here is going to undergo a strain which is identical to the strain undergone by the substrate, the material on which it is bonded. And in fact, we can recognize 2 directions here. One we call as the strain direction, and I call it active. That means, if you subject the strain gauge element to an extension or a stress or a strain in the direction shown here by the vertical arrow here, it will respond. That means, it is going to be active. We will later see why it is so. If however, you were to apply a strain in the direction perpendicular to the straight segments, that means, in the other direction, normal direction, the strain gauge is not going to respond, and therefore, that will be called as the inactive direction. So, basically, the strain has to be in a direction which is coincident with the arrows shown here. It may be either extension or contraction. That means, it may be either extension of the length, that means, that the positive strain, or it could be a compression, which means it is going to be a negative strain. And the strain itself is defined as the original length, the ratio of the length increase, change in the length, divided by the original length. So, it is a ratio, and it has no units. And because the strains which we measure in practice are very small, sometimes we refer to the micro strain. That means, it will be 1 micrometer per meter of the original length. So, in terms of micro strain we can measure, and we will be measuring in the most of the applications, we will be measuring very small deflections, and the strain undergone by this etched material is going to be very small. We will later come to look at the different materials which are used and so on. Before that, let me just show, this is just a schematic, it is not to scale. So, let me just show how a typical strain gauge looks like. So, I have taken it from the web site of omega.com. Omega is a manufacturer of transducers of various types. They also manufacture strain gauge elements, and what I have shown here is a typical strain gauge element, which is consists of the 2 pads from which connection is taken to the outside electronic circuitry. These are the segments which we talked about. The number is determined by the length required for the strain gauge, and in fact, it is determined by the resistance of the element. If there is no strain in the element, it will have a certain resistance. This resistance is the resistance of the strain gauge, which is going to be quoted. There are 2 values which are usually used in practice. One is 120 ohms, which is standard. The next one is 350 ohms. These are two standard values. 350 ohms is larger value, 120 ohm is a smaller value. So, two values are normally used in practice. And you can see here, as is shown here, this material is deposited on a substrate which is in the form of a foil, and the foil will have a backing which is adhesive backing. So, all you have to do is to peel out the paper, and then the adhesive backing is going to be available to be stuck onto the surface whose strain we want to measure. And the adhesive gives enough bonding, or expected to give enough bonding, so that the strain of the strain gauge element is equal to the strain of the parent element, which is subject to the stress, and therefore, it is experiencing a strain. So, what I will do now is to look at the possible way of arranging the strain gauge. Of course, after looking at this arrangement, we will try to see how to characterize the strain gauge and how it is used for measurement and so on. That will come later. So, one arrangement is to have a what is called a pressure tube. Pressure tube is simply a short length of tube, as is shown here, of a thin walled construction. So, you have a radius of the tube equal to r and the thickness equal to t, as you can see here. The radius is r and thickness is t, and normally the thickness is very small compared to the radius. The radius may be about 10 millimeters or 12 millimeters or some such a value, and the thickness could be a few tenths of a millimeter. That means, it could be 1/10 of a millimeter or 2/10 of a millimeter and so on. So, you see that the thickness is going to be very small compared to the radius, and therefore, this cylinder is essentially a thin shell. The assumption is that the cylinder acts as a thin shell, and the active gauge is going to be bonded onto the circumference, as is shown here. So, the longer dimension here for this rectangular piece of element is the active direction. That means, it is going to measure the strain in the circumferential direction, as you can see. That is also called the hoop stress or hoop strain. The direction which is along the circumference is the hoop strain, and we also have a dummy gauge, which means that it is going to be connected in such a way that it is not going to undergo any strain. And how can we do that? Either we can do the following. The end of the tube is closed by a very thick disc. The shell is very thin and the thick disc is very thick. For example, I can have a disc of 3 or 4 millimeters or more closing the tube on the right hand side. When that happens, the strain undergone by the thick disc is going to be very small and negligibly small, and therefore, if I go back to the sketch, the strain indicated by the dummy gauge will be essentially 0. That means, that the dummy gauge resistance does not change during the operation of the instrument. Now, why do we have a dummy gauge? Suppose I have the active gauge here, and suppose the pressure is introduced inside the tube. It will of course undergo a strain because of the hoop strain, and therefore, it is going to undergo a change in resistance because of changing the length, as we shall see in a little while from now, and therefore, the resistance of the gauge is going to change. But the resistance will also change if the temperature of the system changes. For example, if the instrument is located in a laboratory space and the temperature in the laboratory fluctuates during the daytime, the active gauge is going to indicate a change in resistance even when there is no stress, because the temperature has changed, and because of temperature there is expansion. Because of the expansion, it is going to show a change in the resistance. Therefore, if I locate a dummy gauge very close to the active gauge, that means that these two are going to essentially experience the same temperature variations in the laboratory. Both the gauges are going to undergo similar changes in resistance because of temperature, and therefore, the dummy gauge acts as a compensation for the temperature change. That means that the dummy gauge and the active gauge both undergo changes in resistance, similar changes due to temperature changes, and therefore, they are going to cancel each other. Depending on how we are going to connect it later on, we will see the circuitry. At that time, it will become clear how to connect it. So, the pressure tube with bonded strain gauge is a very simple idea. The active gauge is going to respond to the hoop strain, and the dummy gauge is going to respond only to temperature variations, which the active gauge will also do, and the compensation is obtained by having the active gauge and the dummy gauge very close to each other, and the dummy gauge is going to be mounted on a very thick end disc, which undergoes very little strain because of the pressure acting inside. Of course, when I say pressure acting inside, it is delta P. Outside, if it is atmospheric pressure, I will be measuring the P minus PA, and therefore, what I get is the gauge pressure. And a pressure tube bonded strain gauge can be designed for a very large range of pressures, from very small to very large pressures, because it is simply determined by the strain of the tube element and how it depends on the thickness and the radius, and that is all what is there to it. So, let us look at the way it is going to work out. The hoop stress in a thin cylinder, from strength of materials you will have learned this. The hoop stress sigma is equal to P into R divided by T, where P is the internal pressure, or actually the pressure difference between the inside and outside, or the gauge pressure, and the R is the radius of the tube, and T is the thickness. This is for a thin cylinder. When you have a thin cylinder, the stress is essentially uniform across the thickness of the shell, and you get a very simple expression sigma equal to P R by T, which can be very easily derived, but that will be that is already known to you from your strength of materials, where you will have learned some of these things. And the corresponding strain, which we will call as the hoop strain, is simply given by the stress, hoop stress divided by the Young's modulus, and the assumption we are making is that the strain is so small, that the material is within the elastic range. Therefore, the stress sigma will never be very large. In other words, it will be small compared to the yield stress of the material, so much smaller. And therefore, I can use epsilon equal to sigma by E, where E is the Young's modulus for the material, and substituting for sigma the expression P R by T, I will get P R by T into E, and if I know the radius, the thickness, and the Young's modulus, there is a direct relationship between the strain and the pressure. And we will see later that the strain is related to the resistance of the strain gauge, and therefore, I will be measuring the strain, and from that I will be working backwards to find out what is the corresponding pressure which gave rise to it. In fact, I can use this expression epsilon equal to P R by T E to define what is called a gauge factor. That means, epsilon is equal to some constant times the pressure. It is a linear relationship between the strain, the hoop strain, and the pressure, which will be epsilon is equal to P times some constant, which is R by T E. So, I can say that this R by T E is the gauge factor, I call it as GF. The gauge factor is simply given by radius of the tube divided by the thickness of the cylinder divided by the Young's modulus. So, this is basically the way we are going to use the instrument to measure the pressure. So, another example I am going to take before we look at the strain gauge and its theoretical background and so on. We are looking at a strain gauge based pressure cell. Again, I have taken it from the website of omega.com, who is a manufacturer of these kind of instruments, and this is a schematic of how a pressure cell is made, and you can see that this is essentially a cylindrical casing within which you have certain elements. One, you have a low pressure diaphragm on the left hand side. This is the low pressure diaphragm. The low pressure is fed in through the opening here. We have the high pressure P1, and there is a high pressure diaphragm, and there are in fact two of them, and in between there is silicone oil or silicone fluid, which is subjected to the high pressure. That means that when I apply the high pressure here, it is communicated to the silicone fluid in this particular region. When I have the low pressure on this side, the low pressure is going to be communicated to this region, and therefore, what happens is that there is a pressure difference between this side and this side, and therefore, when you apply a pressure here, it is going to undergo a change in the strain, and therefore, it is going to compress the liquid here. And in fact, you can see that the gauge itself is attached to the diaphragm here, and the output from the gauge goes to the transducer electronics, which is outside. Okay. Let us look at some of the features. There is the overload plug. This plug is actually going to sit in this hole, which is connecting the low pressure side and the high pressure side. And if the pressure you apply is very high, more than the rated pressure for which the pressure cell is designed, this is going to go and close this opening, and it will not work after that. Okay. It is going to protect the low pressure side from being damaged when you have very high pressure applied here. So, this is just a safety feature. Now, in other words, you see here that the pressure difference P 1 minus P 2 is communicated to a diaphragm, and the diaphragm is going to undergo a strain, and that strain is what I am going to measure by using the sensor. The sensor is nothing but a strain gauge mounted on the diaphragm, and then what I am going to measure is the deflection, and this deflection is related to the pressure difference P 1 minus P 2. And in fact, I can simply have a calibration done by having a known pressure applied here and a known pressure applied here. I can choose the delta P, and I can measure the delta P using a dead weight tester, for example, or some other arrangement, so that I can have a calibration of the output of the transducer with respect to delta P, and that is one way of using the pressure cell. So, we have discussed, in other words, two types of arrangements. One where I have a tube, a short tube, very thin wall material, and the inside I am going to apply the pressure to be measured, and the tube is going to undergo a strain because of the stress developed in the circumferential direction. In fact, we can also do in the longitudinal direction. There is no reason why you should not do. Actually, the circumferential strain is slightly more than in the longitudinal direction. That is the reason we use that. And the strain is now measured using the strain gauge. So, now let us look at the theoretical background regarding the strain gauge, and for this I am going to go to the board and look at some of the principles. So, what I will do is I will look at the principles of strain gauge, and then look at the different properties which go into determining the performance of strain gauge as a strain measuring instrument. Then what are the different materials which can be used, what are the gauge factors which we are going to get or have in these cases, and then how the measurement is made by using suitable electronic circuitry. This is the basic idea of this lecture. So, let us assume that we have a cylindrical object. For example, it could be a wire. So, I will say this is the length is L and the area of cross section is A. So, I have a small piece of material in the form of a cylinder which has got a length L and a cross sectional area equal to A. This is a solid cylinder. Now, let us assume that it is subject to some changes or some strain because of forces acting on it. Okay. So, suppose I stretch the cylinder, I elongate the cylinder by applying a tensile force. So, the length is going to become, in other words, I am going to change it to L plus dl. This is the elongation. So, elongation is dl due to the action of a stress or force in the axial direction. This is the axial direction. So, what will happen when you have a elongation in this direction is that in the lateral direction it is going to undergo a change in the dimension. Actually, it is going to reduce in size. Normally, it going to in most materials is going to reduce in size. There are exceptional cases where the size actually increases in the other direction. We are not interested in that. What we are interested in finding out what happens in the case of a material which is going to undergo a change as shown here. So, the delta L dl by L is the strain in the length direction, and let us say dA by A is the change in the area per unit area in the normal direction. Okay. So, this is dA by A is nothing but the strain due to the strain in the perpendicular direction, perpendicular to the direction of the longitudinal strain, there will be change in area. This is due to in the perpendicular direction. A very simple theory which we can look at is the case of an incompressible material. This is not necessarily correct. Suppose we do that, let us assume that the material is incompressible. That means, what does it mean? It means that the volume which is equal to the product of L and A is constant. Okay? The volume remains constant. That means, when you have a deflection or change in L, A will automatically change such that the total volume is going to remain the same. So, we can do the following. So, I will call this as constant equal to some V, which is equal to, let us say, V naught. So, we will say dV naught by V naught equal to 0, and by logarithmic differentiation, which is familiar to us, this will be nothing but dL by L plus dA by A, and therefore, this is equal to 0. That means, dA by A equal to minus dL by L. That means, that the positive strain in the longitudinal direction leads to a negative strain or negative change in the area of cross section. It becomes longer, the cylinder has become longer, or any cross section. In fact, it is not necessary to have a cylinder. You can have a prism, you can have a square bar, it will same thing is going to happen. The cross section is going to become smaller and the length has become larger. And conversely, suppose I subject this material to a compression, the length is going to reduce, the area is going to increase. Okay? And I am looking only at very small changes. Let us not go close to the yield stress and so on. We are talking about very small changes in the length and the area of cross section. We are not talking about large changes. Now, let us look at the case of normal materials. The one I talked about is a incompressible case, and most materials are not necessarily incompressible. So, if I have a strain in the longitudinal direction, so the lateral strain divided by the longitudinal strain. So, I am looking at two different strains. This ratio we call as the Poisson ratio. Poisson's ratio. This particular value of nu is anywhere between 0 and 0.5 for most materials. There are exceptions, as I said earlier. There are materials for which it may not be in this range, but we are not interested in such materials in most cases. And most materials, if let us look at that, let us look at the consequence of that. So, if I have a lateral strain equal to divided by longitudinal is equal to strain nu. So, we can see what is going to happen in the case of what we had earlier. So, we talked about a strain in the longitudinal direction. Now, we have talked about a change in area. Now, let us look at the strain in the longitudinal direction is nothing but dl by L, and in this case if the original radius is r, the radius is going to become smaller. Okay. Now, I can write the value of A is the area of cross section is pi into r squared, and therefore, dA equal to 2 pi r dr. I am again assuming very small changes, and therefore, I can even use the differentiation to indicate the changes. Okay, dA equal to 2 pi r dr. Therefore, what I want is dA by A. So, I can write the dA by A by dividing. So, I will write dA by A here. dA is 2 pi r dr divided by pi r squared. So, pi will cancel, 1 r will cancel, it is 2 dr by r, very interesting and important thing to remember. The lateral strain is dr by r is nothing but the lateral strain, and the change in the area, the strain in the areal strain or area strain in the area is simply twice the lateral strain, and we know that dr by r is equal to Poisson ratio times dl by L, and therefore, I can write this as 2 times nu times epsilon, I will say L. Epsilon L is the longitudinal strain, I will say this is epsilon, or I will avoid using the subscript, it is not necessary. So, I will just say epsilon. So, if epsilon is the strain in the longitudinal direction given by dl by L, then the change in the area or the strain in the area is given by 2 nu times epsilon. So, with this background we can write the following. So, with the Poisson ratio introduced here, we have dA by A equal to 2 nu times epsilon, and where dl by L is equal to epsilon. Now, let us look at the material of a strain gauge. So, I want to now link up whatever we talked about in general about any material which is undergoing a strain, the longitudinal strain and the lateral strain. I am going to now look at what is the consequence of the strain gauge. The strain gauge has a material which has got a resistivity equal to rho. Let me just introduce the resistivity. We are talking about the electrical resistance of the material. The material is usually a conductor with a specific resistance or resistivity equal to rho, which is in units of ohm meter. So, the length of the conductor is L, and the area of cross section is A, area of cross section. Okay. So, I can write the for the resistance R, if I want to indicate that is electrical resistance, because R was also used for the radius of the cylinder, I will just call it a resistance, electrical resistance Re is given by rho into L by A. This is a familiar expression which we know from our elementary electricity. So, now what is the change in the resistance? I can again use a logarithmic differentiation. So, logarithmic differentiation if you use, you get DRE by RE. What do you mean by logarithmic differentiation? I take the logarithm both sides, it becomes log RE equal to log rho plus log of L minus log of A. And now I differentiate term by term. This gives you 1 over RE DRE, that is what I have in the left hand side, 1 over rho d rho plus dl by L minus dA by A. This is what we have. So, DRE by RE is the ratio of the resistance change to the original resistance. So, we are treating ratios in all these equations, and the ratios are non-dimensional, that means they do not have any unit, and therefore, the left hand side is a change in the resistance with respect to original resistance equal to change in the resistivity, which may be due to either pressure or temperature, because pressure and temperature also have an effect on the resistivity of the material, and we will come to that in a few minutes from now, plus the change in the length with respect to its own length dl by L is the ratio, minus the change in the area divided by the original area. So, we have 3 terms contributing to the change in the resistance. So, what I am going to do actually in the measurement using the strain gauge as a measurement as a transducer for measurement of strain is to change, note the change in the resistance with respect to the original resistance. So, it is just like strain, original length divided by length is the strain, mechanically we call it the strain. In the case of resistance, it is the change in the resistance divided by the original resistance. So, the right hand side, the changes in these quantities lead to a change in the resistance. This is the basic theoretical framework on the strain, on which the strain gauge is going to work. Now, I will combine this equation with what we have seen earlier. If you go back to the previous one, I have got dA by A equal to 2 nu times epsilon and dl by L equal to epsilon. So, all I have to do is to put them together. Actually, I should have done a minus sign here. You will appreciate that if you go back here, you will see here that dl by del is positive, dA will be negative. We saw that in the here minus dl by L. So, that has to be introduced, and therefore, dA by A is equal to minus 2 nu epsilon, dl by del L is epsilon. So, all I have to do is to introduce these two into that equation, and you will see that dRe by Re d rho by rho plus dl by L is epsilon plus 2 nu epsilon, or I can write as d rho by rho plus epsilon into 1 plus 2 nu. If a nu equal to 0.5, this term will become 2 nu is 2 into half is 1, 1 plus 1 2, 2 into epsilon 2 epsilon. So, you see that in the case, this is actually the incompressible material case, incompressible material. For an incompressible material, d Re by Re, dRe by Re becomes d rho by rho plus 2 epsilon. Okay. So, you can see that this 2 is the factor which links the change in the resistance divided by resistance equal to 2 epsilon, and therefore, you can see that epsilon is equal to half of dRe by Re. So, epsilon is equal to half of dRe by Re. So, this factor 2 is also referred to as the gauge factor. And for an incompressible material, the gauge factor happens to be equal to 2. Of course, I have not looked at the d rho by rho yet. D rho by rho, this quantity can be due to changes in pressure or temperature. So, that is why the dummy gauge is going to bring this extra term d rho by rho is going to be there, because the temperature effect is also there and the pressure effect is also there. Of course, this may be very small in normal practice, and therefore, it may be safe to ignore this. Sometimes we may ignore, in which case dRe by Re becomes simply equal to epsilon into 1 plus 2 nu. So, this is basically the idea about. So, in fact, we can define the gauge factor in more complete terms. This is called the gauge factor. It is given by 1 plus 2 nu plus d rho by rho divided by epsilon. D rho by rho by epsilon, which is nothing but dr by Re epsilon. This is the ratio we call it as the gauge factor, and for materials which are having a value of nu equal to 0.5, Poisson ratio equal to 0.5, this will become 2 plus this small quantity which we normally would be ignoring, it will become equal to 2. So, the gauge factor is roughly equal to 2 for many materials. We will see what are the materials which are used. Many materials which are actually used as strain gauge elements, that is very important. In other words, we use materials which have a gauge factor roughly equal to 2 in most of the applications. So, let us go back to the presentation, where I have some information on the Poisson's ratio typical values for many materials. Steel is a very popular material for diaphragm, for example. I am not now talking about the, I am talking about the strain gauge is one side, one thing, the element which undergoes strain is also there. The strain, the diaphragm, for example, the Poisson ratio typically for steels is 0.3, concrete for example is 0.2, gold 0.42, you see that it is closer to 0.5, glasses may have between 0.2 and 0.25, some elastomers have equal to 0.5. There are some materials which even have negative Poisson ratio and so on. Let us not worry about those things as far as we are concerned here. Now, let us look at some of the materials which are used in practice, and they are given in the form of a small table. I have taken it from the same omega.com website, where this particular table is available. So, some materials, typical materials, platinum for example, 100% platinum, the sensitivity or gauge factor is 6.1, it is not equal to 2, much larger. Platinum iridium, 95% platinum, 5% iridium. Some of these materials you already have seen were also candidates used in thermocouple manufacturing. So, they are also used in other sensors. So, that is a common feature between some of these materials. Platinum RTD resistance thermometers are made of platinum 100%, and they have a sensitivity of 6.1. Platinum iridium 95%, 5% iridium 5.1. Platinum tungsten 92% platinum and 8% tungsten 4. And then you see here I have shown some with a yellow background. These are very common materials used in practice. Constantan is also given the name advanced, some people call it copal. These are actually the names given by the manufacturers, and they consist essentially of nickel 45%, copper 55% alloy, and the gauge factor you see is very close to 1, very close to 2, 2.1 here. Nichrome, nickel 80% chromium 80%, it is called nichrome V or 2.1 again. There is something called karma. I think it is not coming out right in this thing. This KRMA. It is nickel 74%, chromium 20%, aluminum 3%, iron 3%. It is again 2. There is something called armor D, iron, chromium, aluminum. Again you see it is close to 2. And then we have monel, nickel and copper in 67% and 33%, we have 1.9. So, you see that the most of these materials which I have indicated here, these 1, 2, 3, 4, 5, these are normally used in practice for making the strain gauge material. Other materials are just included just to indicate the kind of sensitivities you will expect from these. So, with this background, let us go back to a discussion on the further on the use of the strain gauge. For this purpose, what I am going to do is I am going to give without proof some of the expressions which are useful, and then I will take up a simple example and work it out. That is what is possible in the amount of time we have in this particular lecture. So, let us do that. So, if you have a diaphragm, I think I referred to it earlier in the last class itself, last lecture itself. You have a diaphragm which is fixed at the periphery, and it has got a radius of A and a thickness equal to T. This diaphragm is subjected to a uniform load. That means that pressure is acting on the two sides. One side is high pressure and the other side is low pressure. So, the diaphragm is going to undergo a change in shape. So, we expect something like this to happen. And at the center, you are going to have the maximum deflection. And at the periphery, because it is held fixed or clamped, there is no displacement. It is clamped here. Actually, if you look at it, it will be a circle which I fix it here, fixed at the periphery. And I am talking about the deflection at the very middle of that circular diaphragm of thickness T, radius A, and let us assume that E is the Young's modulus and nu is the Poisson's ratio for the material of the diaphragm. Okay. We can show that from again for small deflections. What do we mean by small deflection? It should be small compared to a characteristic dimension of the diaphragm itself. For example, the change in the movement which I have shown here must be smaller than the thickness. Okay. It will be in fact much smaller than the thickness and much smaller than the radius of the diaphragm itself. Therefore, for small deflections, we have a linear relationship between the pressure and the deflection. So, Y max is given by 3 p a to the power of 4 multiplied by 1 minus nu squared divided by 16 E t cube. So, 3 p a to the power of 4 into 1 minus nu squared divided by 16 E t cube. So, this is a very important relationship. Actually, you can write it as, if you rewrite it, is equal to sum k times Y max. So, what am I going to do in my practical application? I am going to measure the Y max, and if I know the gauge factor k, which is nothing but, you can see here, p is equal to k times Y max, k is nothing but 16 E t cube divided by a to the power of 4 into 1 minus nu squared. So, you see that this gauge factor is given in terms of the geometric and the physical parameters. Geometric parameters A and T are the geometrical parameters, the radius and the thickness, and the Poisson ratio and the Young's modulus are the properties of the material, physical properties of the material, and the geometric parameters are going to combine together to determine the value of K. And this is a linear relationship under the assumption of for small deflections that is going to hold good. Therefore, I can use this expression as long as the deflection is very small. So, let us remember that. The second formula I am going to give is something which is going to be useful, the natural frequency of the diaphragm. Natural frequency of the diaphragm. This will play a role in measurement of transient pressures when the pressure is varying with respect to time. So, the natural frequency is given by F natural is again for small deflections it is 0.469 T by A squared and under square root of E by rho into 1 minus nu squared, where rho is the density. This will give you the value in hertz, all others are in SI units. The lengths are on meters, Young's modulus is in Pascal, nu is the ratio, therefore, it will have no unit, density will be in kilograms per cubic meters, thickness in meters, the radius also in meters. So, if you substitute, you will get the value of the natural frequency in hertz. Now, let us look at what we are going to do in the case of a gauge. So, if you look at the gauge, look at the diaphragm, I will write the diaphragm like this, and the gauge, if you remember, look like this. Just a schematic. From here I have taken the output leads. So, there is a gauge attached to the diaphragm in the middle, and this is a radius equal to epsilon A, thickness T, and the gauge has got a certain physical thickness, physical size. It is not a small thing, it is a, you saw the picture I showed, it is quite a big thing. So, it is going to occupy a certain region on the diaphragm, which is not a point, but a certain area. Therefore, we can expect that the gauge is going to actually respond to the average value of the shear, the average value of the strain over the area of the gauge, Okay. So, we can say that the gauge responds to some mean value. It is not the maximum deflection, it is the mean value of the strain over the area, over its own area. So, useful formula has been worked out for the value, the gauge response, assuming a gauge factor of 2. You remember the gauge factor equal to 2 if you take, which is true for those 4 materials I discussed earlier. For those materials the gauge factor is 2. If I do that, the average value of the gauge output in terms of millivolts per volts, okay, this E naught is the gauge output in millivolts per volt. I will explain it a slightly little later. This is given by 0.75 P A squared into 1 minus nu squared divided by T squared multiplied by E into 10 to the power of 3. So many millivolts per volts. Okay. So, the gauge responds according to this formula, because this is obtained by integrating the effect felt by the gauge over the area of its own area when it is placed on the surface of a element which is undergoing strain or deflection. So, this is the background for the physical aspects of the problem. Now, let us look at the, before we take up the example, I will look at the way we are going to use the strain gauge in a circuit. So, I will be able to just discuss few elementary things, and then of course, we will continue it in the next lecture. So, basically what we are going to do is to use a Wheatstone bridge, which is very familiar to us. So, let me just give a brief idea about the how it is going to be used. So, we have 4 resistances. We have already seen some of these kind of things in the case of temperature measurement also. We will label them as R1, R2, R3 and R4, and I am going to inject some voltage from outside, positive, negative, and I am going to measure the voltage here. This is positive, this is negative. We will call this as voltage is Vs, the supply voltage, and Vo is the output. So, Vo is equal to output, Vs is the supply. I am talking only about DC volts, that is why I have shown a battery here, or it could be a supply of DC voltage. In fact, we can show by simple analysis of this circuit that the relationship between Vo and Vs is given by the following formula. I will not derive it, it is very easy to do that. So, we will say that V naught divided by Vs, the ratio of the output voltage to the supply voltage is given by R3 R1 minus R2 R4 divided by R2 plus R3 into R1 plus R4. This is a very important equation. It gives us an idea about the ratio of the output voltage, which is in the numerator, to the supply voltage is given by R3 R1 minus R2 R4, and if you can immediately see that when there is a balance, the condition is R3 R1 equal to R2 R4, then V naught equal to 0. This can also be written as R3 R1 by R4 is equal to R2 by R3. So, R1 by R4 equal to R2 by R3 is the condition. Now, suppose we have the following. We have a gauge with 120 ohms value for the resistance. Suppose I choose R1 equal to R2 equal to R3 equal to R4 equal to 120 ohms. It will be in balance to start with, and what I will do is I will identify this R3 as the variable resistance, which is the strain gauge. So, one of the resistance has been replaced by the strain gauge, and this is called a quarter bridge arrangement. So, this is called the quarter bridge arrangement. Quarter bridge because 1/4 of the bridge consists of a variable resistance. So, what we will do is to continue from here in the next lecture, look at the way this is going to respond to the changes in the pressure and therefore, the changes in the strain, and then we will look at how to interpret the information in terms of the pressure which is being measured. Thank you.